Good day, everyone. We are from Group 3 Electronic 4th Lab, and today our team will be presenting our project, a comparative study of BJT and FET amplifiers for sensor signal amplification. So in this presentation, we will explore how these two distinct transistor technology handle weak sensor data and evaluate which perform better under various constraints. Next. So to give you some background, signal amplification is a fundamental process in electronics. Sensors often produce incredibly big output that are highly susceptible to noise. Because of this, amplifiers play a critical role in preserving signal integrity before the data is processed by microcontrollers and analog to digital converters. So as shown in our data acquisition system diagram, the signal conditioning phase bridge the raw physical sensor to the digital processor. So for this task, we look at two main choice BJTs, which are current control device offering high current gain, and FET, which are voltage controller device praised for their low power consumption. Next. And our research targets three primary application domains where this technology is vital. So the first one is smart monitoring, where we amplify low-level signal from the temperature and pressure sensor for accurate medical or environmental measurement. In agriculture, where we focus on enhancing weak sensor signal in soil moisture and environmental monitoring system to optimize crop yields. And number three, industrial IoT, where improving signal quality is key for reliable process control and machine condition monitoring in remote nodes. Next. So to guide our study, we have established three core research objectives. So the first one is theoretical analysis to deep dive into fundamental operating principle, biasing mechanism, and specific characteristic for both BJTs and FETs. Second, design and simulation, where we will design and simulate a BJT common emitter and FET common source amplifier using multisim software. And finally, a comparative evaluation to directly judge this topology based on critical metrics like voltage gain, input and output impedance, thermal stability, and overall cost effectiveness.
Next, I will briefly introduce what is BJT. BJT is also known as bipolar junction transistor, which consists of three-terminal semiconductor device. It is used for amplification and switching. BJT consists of three regions, which is emitter, base region, and collector region. Emitter is used for inject current, inject charge, and base is control their flow, and collector is collect the carrier. Next, the types of BJT classified into two types, which is NPN and PNP. NPN is use electrons as a majority carrier, while PNP is use holes. And next, the operating region of BJT. BJT divided into three regions, which is cutoff region, active region, and saturation region. In cutoff region, both junction is reverse bias and it behave as open switch. While active region, the emitter base junction is forward bias and collector base junction is reverse bias. It is function as amplifier. While the saturation region, the both junction is forward bias, it is behave as closed switch. And the current gain, which is also known as beta, is the ratio of collector current and base current. Beta is used to determine amplification capability. A larger beta value indicates that a smaller base current can control a larger collector current, and beta depends on transistor types and operating condition. And this is the output characteristic curve of BJT. The graph shows a relationship between collector current and collector emitter voltage. The difference curve corresponds to different base current. The graph is used to identify saturation region, active region, and cutoff region.
Good day, everyone. Today I will be presenting on FET. And FET is a fundamental voltage control device. As you can see, there are two main families we are discussing today, which is FET and MOSFET. And for JFET, there are two channels, which N channel and P channel. And for the other MOSFET, we got D-type MOSFET and E-type MOSFET. Next, we'll start with the operating modes. First is the depletion mode. You can think that it is a normally on switch at 0 gate voltage. A physical channel already exists. As we apply a negative gate voltage, the depletion region expands, increasing resistance and narrowing the conduction path. This is the standard for all JFET. Next, in contrast, we have the enhanced mode, which is normally on. And here, no physical channel exits at 0 volt. We have to apply a gate voltage higher than the threshold to induct an inversion layer and activate the enhanced conductivity because it draw particle zero power in standby. This mode is the fundament of modern CMOS technology and microprocessor. Next. So FET operate in these three regions, which is the cutoff region, ohmic or linear region, and saturation region. Next. In the cutoff region, the FET is completely off. For an enhanced MOSFET, this happens when our gate source voltage is less than the threshold voltage. The channel simply doesn't exit, and the device act like an open switch with zero drain current. Next. Next is the ohmic or linear region. Here the FET is on, but the VDS is very small. In this state, the FET act like a variable resistor. As you can see on the graph, the ID is currently is increasing linearly with the drain voltage. Next. Let's look at what drives FET performance. The output voltage ID is controlled by a very small input voltage VGS. The voltage control naturally gives FET several major advantage. Next. A key in here is GM. This measures how effective the gate control the drain channel. This can be defined mathematically as the graph as the formula given. So a higher GM means the FET provide more gain. Next. The other major factor is input impedance, Z-in. Because the gate draw particularly current, the input impedance of is infinity. JFET sits around 10 to 19 ohms, while FET exceeds 10 to 12. This ensures the FET don't pull current or lose the preceding stage of a circuit preventing signal integral. Next. The reason MOSFET achieve such extreme input impedance is physically. So you can see they have a thin layer of silicon diodes insulate the gate. Next. Now let's look at the characteristic curve. The transfer characteristic curve plot drain current against gate source voltage. As you can see on the graph for a JFET, as the gate voltage becomes more negative, the ID drops steadily until it reaches cutoff. Next. The output characteristic curve maps drain currents against VDS. Beautifully, the three regions we discussed earlier. The lower ohmic region on the left, the flat saturation region on the right, where the pit off occur, and the zero current cutoff region at the very bottom. Next. And this is the sum up of the JFET and MOSFET. Next. In conclusion, FET remains a cornerstone of modern electrons due to these three advantages: high gains, total isolation, and incredibly efficiency with a low power consumption. Thank you.
For my part, I will explain the BJT amplifier design. In this design, we use two N3904 NPN transistors in a common emitter amplifier configuration. This configuration was selected because it can provide voltage gain and is suitable for small signal amplifications. The circuit use voltage divided by years the circuit used the voltage divided by years with R1 47 kilo ohms and R2 10 kilo ohms to get the voltage base. And for the voltage emitter, we use what we learned in the class, VB minus VBE, and we will get the answer VE. And for the collector voltage and also same, just sub into the formula and we will get the answer. In DC analysis, emitter current, we use the normal formulation V equals to IR, so we can get this formula, and you can get the emitter current is 1.41 milliampere, and collector current is assumed similar as emitter current, so also same 1.41 milliampere. And Q point, we can get the answer is IC equals to 1.41 milliampere and VC equals to 7.49 voltage. In conclusion, VC is between 0 voltage and 12 volt voltage, so the BJT is in a active region. Next. For input resistance, we use a parallel circuit, so we can get the input resistance is 8.25 kilo ohms, and output resistance is similar as a collector resistance, so it is 2.2 kilo ohms. And for AV, voltage gain was calculated as negative 2.2 kilo ohms. So the negative sign means the output signal is inverted, so the output has a 180-degree phase shift compared to the input. Next. Finally, we use multi-system using a 10 millivolt and 1 kHz sine wave input. The simulation showed that the output signal was amplified and inverted. Therefore, the calculation and simulation both confirm that the common emitter amplifier works.
Very good. Good morning, guys. So for me, I will present my FET amplifier design. Okay, so this is the circuit that I designed. So for this project, I select a 2N7000G N-channel MOSFET as an active device, and the circuit is powered by a 12-volt DC supply. And for the 1 mega ohms resistor R3 and R4, for the voltage divider to bias the gate at approximately 6 volt, the 1.5 kilo ohms drain resistor act as the load, and while the 1 kilo ohms source resistor provide a self-bias stabilization. Finally, a C1 and C2 are coupling capacitor that block DC and allow only the AC signal to pass. So next please. So this is the all component that we use inside the circuit design, and you can see the all is the details. Okay, so the next. So this is basically how we get the values from the circuit, and yeah, we're using the formula V equal to GS. We need to find the VGS first, so we get the result is 2.51, and we also need to find the VTH, which from the theoretical, which already given inside the circuit is 2.1 volt, and we compare it, and we get the VGS is larger value than the V theory. So it's proof that the MOSFET is on. And the next step is we need to find the VDS, and the VDS is basically just the V minus the EVS. So we get a 3.27 volt, and we compare it with the VGS minus VTH, the value that we get just now, and we compare it, and we prove that the VDS is larger than the VGS minus V theory, and the MOSFET is operating in the saturation active region. Next slide. So after that, we can get this is the result graph from the multi-sim simulation. And for the first graph, it showed that gate voltage V2 which center at approximately 6 volt with a small 10 millivolt AC input signal. And this can confirm that the gate bias network is working correctly. And for the second graph is a source graph, source voltage, which remain around 3.49 volt with only a small AC variation, and this indicates the source resistor provides stable biasing. And for the third graph is the output waveform after the coupling capacitor. The capacitor removed the DC component and leaving only the AC output signal. So overall, based on these three simulation results, we can get a theoretical calculation and confirm that the amplifier is functioning properly. So in conclusion, the common source of MOSFET amplifier was successful design and simulate, and the biasing network established a stable Q point. The MOSFET operate in the saturation region, and the simulation result was consistent with the theoretical analysis. Thank you.
Okay, hi guys. Next is my part. So I'll present about comparative analysis between BJT amplifier and FET amplifier. So this comparison is based on several important parameters. First, the FET has a much higher input impedance, which is about 500 kilo ohm, compared to the BJT, which is only 8.25 kilo ohm. So this means the FET draws almost no current from sensor and causes much less loading on the input signal. So second is output impedance. The FET has a slightly lower value of 1.5 kilo ohm. So while the BJT has only 2.2 kilo ohm. So next is based on our multi-sim simulation. The BJT amplifier achieved a voltage gain of approximately negative 2.2, while the FET amplifier achieved a practically gain of about 1.25. So therefore, in terms of voltage gain, the BJT amplifier performed better in our design circuit. However, the FET has several other important advantages. Since the MOSFET gate draws almost zero current, it consumes less power than the BJT. So it also provides better thermal stability, faster switching speed, and better performance when connected to high impedance sensors. So in terms of cost, both transistors are inexpensive and widely available. So cost is not a major deciding factor. Overall, the BJT is suitable when higher voltage gain is required, while the FET is more suitable for sensor interfacing because it offers high input impedance, low power consumption, and better signal preservation. Next, so I will go back to the previous slide. Okay, so our final recommendation based on our comparison, we can recommend using the FET common source amplifier for the sensor signal amplification application. So although the BJT amplifiers provide a higher voltage gain, the FET offers several advantages that are more important for sensor system. These include very high input impedance, low power consumption, better thermal stability, and minimal loading on the sensor output. This characteristic make the FET especially suitable for IoT devices, battery powered system, and applications that require accurate amplification of weak sensor signals. So therefore, the FET is preferred choice for modern sensor signal conditioning. So conclusion, both amplifiers successfully amplify weak signal. The BJT provides higher voltage gain, while FET offers better efficiency and better performance for sensor interfacing. Therefore, the FET is preferred choice for modern sensors signal amplification. I think that's all for our group. Thank you.